Hello, everyone. My name is Mehul Motani. I'd like to welcome you to the third talk in 2021 of the seminar series, Information Theory in Singapore, ITIS. And also, if you're here for the first time, welcome to Singapore. Well, I guess virtual Singapore. I wish I could greet you in person, but these are strange times, so this will have to do. Behind me is a picture of the Singapore skyline and Marina Bay for you to enjoy. So I'll take a view. There is Marina Bay Sands, and right. So I hope this pandemic passes soon, and you all can visit Singapore and see the beautiful country for yourself. Now let's get on with it. So the Information Theory in Singapore seminar is brought to you by a team that includes Han Mao from NTU, Tsai Kui and Tang from SUTD, and me from NUS. Our aim is to promote, advocate, and spread the joy of information theory and coding theory within Singapore and around the world. After this talk, there are two more talks for this half of 2021. Before we get going, let me just address a few logistical matters. Please keep your microphone on mute and your video muted for the duration of the talk. If you have questions, you can post them to the group chat, and we'll address all questions in the Q&A at the end of the talk. Now, it is my great pleasure to introduce Professor Emina Soljanin as our speaker today. Let me give you a brief introduction to Emina. So Emina is a professor at the Department of Electrical and Computer Engineering at Rutgers University. Rutgers is in New Jersey in the United States. Emina joined Rutgers in January 2016. And before moving to Rutgers, she was a distinguished member of technical staff for 21 years at the Mathematical Sciences Research Center, MSRC of Bell Labs. Bell Labs has gone through a variety of name changes and is now known, if I'm not wrong, as Nokia Bell Labs. Her interests and expertise are wide, currently ranging from large-scale data storage and distributed computing to quantum information science. She is a 2017 outstanding alumnus of Texas A&M School of Engineering. She's an IEEE fellow, the 2011 Padovani Lecturer, and the 2016-2017 Distinguished Lecturer for the IEEE Information Theory Society. She also served as the president of the IEEE Information Theory Society in 2019. Now it is my honor to have my colleague and friend, Emina Soljanin, share her thoughts with us today on service rates in distributed systems with redundancy. So everyone, please let us warmly welcome Emina. Emina, please.
Thank you very much, Mehul, and thank you, Han Mao, and all colleagues in Singapore for inviting me. I'm very happy to be able to give this talk remotely, but anyway, I feel like in the company of friends. So let me just minimize this window here. Okay, something is not working. Okay, let's see how it goes. All right, well, I'll give you a little bit background about this talk. What I'm showing here is a fountain where you can get various drinks. And when I say service, it might be helpful to think about this water, or actually this pink liquid coming into this glass. So the service is actually delivery of this liquid to the glass, except in our case, is not liquid, is bits. And they're not physically going anywhere, they're being copied to a user who wants to see, who is after some content. And the user can be someone downloading a movie, but it can also be someone, a computer application, for example, accessing the storage layer in a computing system. And similarly, as in pouring this water, there is some speed associated with water going in, right? With liquid going in the glass. If it's too fast, then you would have this maybe ice get out, splatter around. And if it's too slow, you would be probably annoyed. And think about streaming. There is usually some speed that you, some rate of receiving bits that you want to keep. Here, the fountain is showing many drinks. We are actually going to have only one in this talk. There are various generalizations of the problem where you can include many drinks or multiple content. I will precisely define all of these. This is just a little bit to get you start thinking about the problem. So this is joint work with many people. My student here happened to be first because his name starts with an A, so they're listed alphabetically. And he has just graduated, actually no, he has graduated a year ago. Many other people who are here are either past collaborators, Bell Labs interns, even student visitors, and some of them I met through conferences I organized for women and or in Dachstuhl and Oberwolfach. So I'm not going to tell you, of course, about all the work we did together, but since this is kind of a tutorial or a review talk, I thought I would mention all of them. Okay, here I have a distributed service model. So there are n nodes, and a node is this entire fountain, right? This entire box. So n nodes, and they provide service to multiple concurrent users. And that can be some kind of a server at the cloud edge, providing streaming or download or computing, for example. At each node, we distinguish between two functional components. One is for data storage, and the other one is for service, for processing requests. And here, there is, again, comparison of two service models. One is these nodes can serve multiple users at the same time. See, there are here multiple classes. And there is also a possibility that a server can only serve one user at a time, right? So if you're familiar, and some of you in the audience, I know you are, with the batch codes, think about batch codes as a special case, as this right-hand side machine, which is sort of a special case of the left-hand side. Right? And we'll talk about that more. And so now here are some serious definitions. So I have k equal size data objects. They can be k different movies, or you can think about them as just k bits, right? And they're redundantly stored across n nodes. So you don't store a bit on a server, but just think about it that way, mathematically. So all servers have a storage capacity of one data object. And data objects are represented as elements of some finite field. Again, if you don't know what it is, just think about a bit. And each server stores a linear combination of these data objects, which are elements of the field. So you can make a linear combination, and what you get out when you linearly combine elements of a field, you get another element of the field, which is a data object of the same size. And again, if you think about bits, think about XORs. So on your nodes, what you're storing are maybe some XORs of your bits. So a data objects can be recovered from, if it's stored as it is, can be recovered like that, or can be recovered from multiple sets of coded objects, right? And a set of stored objects that can be used to compute a given object is referred to a recovery set for that object. And we have denoted them here as RI1 for object I. And the best way to understand this is through this example. And this example is saying that I have three data objects, A, B, C, and then I have a node which makes an XOR of A and B, and then a node which makes an XOR of A and C, and B and C, and all of them. And some of you will recognize this as a 7-3 simplex code, right? Which maps these three data objects into 7 coded objects. And if I want to recover A, I can either read A Or I can read B and A plus B and XOR that, and still I get an A. Or C and A plus C and XOR that, and that way I get A again. So these are these 4 ways to recover A. Okay, so hold on that thought for the moment, and let me get to the other component of my node, and that's the component which is connected to service. And there are many models that we can have that are mathematically equivalent, and I'm going to talk about 2. And one is a bandwidth model, and the other is a queuing model. And in this bandwidth model, and that's kind of similar to the fountain drinks that I was explaining. You have a bandwidth, some input-output bandwidth that the server has, and download bandwidths of each user are much smaller, and so you can serve simultaneously mu users, and they share this bandwidth W, so they share resources. In the queuing, and again, some people are more, usually engineers are more familiar with, or even computer science with the bandwidth model, whereas performance analysis people are more familiar with queuing. In the queuing model, you have a server that will handle requests for download or computing or any servers at rate mu. Meaning he can complete on average mu jobs at a time per unit time. And if the queue is not, if the server is busy at the moment the job arrives, then that user or job will wait in a queue. And in both cases, if this was the only thing you have in the system, only one node, not multiple nodes, you can only serve the number of users that are smaller than this mu, right? Because that is how many you can do a maximum. So if you have k objects, we assume that in the queuing model, objects arrive at the rate lambda I. And in the bandwidth model is that the number of requests for object I is lambda I. And again, if this is the only one object and one server, you can handle requests that arrive at the rate lambda 1 that is smaller than mu, or you can serve simultaneously lambda users, and that has to be smaller than mu. So now putting this all together, if you put together the it's called the service part, and so the service part is this queue here, and the storage part, this is sort of how it looks like. So there is some request for object lambda I that comes, or you could say lambda I users come, and you can send some of these requests to the server that stores A. Some of these you can send them to 2 nodes, the one that stores B and A plus B, and so on. So you can partition your lambda A into 4 groups, lambda A1, lambda A2, lambda A3, and lambda A4, and direct these groups or allocate them to particular recovery groups. And that's why we call that request allocation. So you split lambda A into these 4 groups. And this is if these A users are the only one using the system. But you may be competing for resources with B users and C users, meaning people who want B movie or a C movie, right? So what do you do then? And that is what this is about. Most big part of this talk is about. Okay. So here is a definition of what we call a service rate region. It's going to be a set of all vectors. Now I have demands for object 1 to object k that can be served by the system. So lambda I is the request for object I, and lambda ij is the portion of this lambda I that you direct towards the recovery group J. What we had here is lambda I, and then lambda A2 you directed towards recovery group 2. And now we are not only talking about I, but about A, but about all of these I, and I's from 1 till k. And And so now I can define this service rate region, right? I know what these requests have to satisfy. And that is, oh, sorry. First, I have to be able to serve all requests, right? And this is this condition 2. So all of these that I was directing towards different groups together have to sum to lambda. Otherwise, I cannot serve lambda, right? So I have to be able to allocate them, and each particular fraction has to be, I have to be able to serve. What does it mean I have to be able to serve? Well, that means that no server is assigned request in excess of its service rate. Meaning that if now I look at some server L, right, L here, and they have n servers, then I look at all objects in the system, and some fraction of the request of each one of these objects is directed to that server L. And I have assumed that they all have a capacity mu, but I could have, for simplicity, I'm even later going to assume that mu is 1. I could have put ML here. So if I go back to this picture, if I now have requests for B, I can do similar thing for B, but there will be each of these servers, each of these nodes will also be asked to provide something to satisfy the B requests. So therefore, when I add them all up, I have to they have to be below the capacity of that server. So this is what we want to find. Like, what is the service rate region? There are some other problems which I will mention. Actually, there are many problems in connection with this. And here is an example. So don't worry about these dots. I will explain what they are later. But right now, let's just look into 2 systems. One system has 3 servers, n is 3. This is system 2 has 4 servers. And in this system with 3 servers, each of these servers has a capacity 8. And in the system with 4 servers, each of the servers has a capacity 6. So 4 times 6 is equal to 3 times 8. So the total capacity of these is 24, so identical. So if I just store one object, there is this system that just provides service to A, I could serve 24 users in one or the other, right? But if I implement some code, which is some map, things change. So one thing that I can do is, when I have 4 nodes, I can, because I have 2 objects, A and B, I can put 2 A's and 2 B's. And since I have 2 A's and each one of them, and this is for the 4 nodes, A, B, B, and each of the nodes can serve 6. Therefore, 2 A's can serve 12, and 2 B's can serve 12. So this entire region and everything that is below that can be served. So if you look at this kind of grayish square here, this is when I have these replication AA and BB. If I have only 3 servers, I cannot replicate both. I can replicate either one or the other, AB, B, or AAB. So I can replicate one of these. And therefore, I have kind of this rectangular things. So this is a 3 server example. For example, look at the blue one. And there, each server has capacity 8. Therefore, whichever I serve, I have only once can serve up to 8 users. And the one where I have 2, like 2 B's here, I can serve 8 plus 8, which is 16 users. But then interesting things happen when I have A, B, and A plus B. So this is with 3 servers, like I have A, B, and A plus B. And I can serve anything in this region here, which is bounded by this purple line, anything below that. And I will tell you how that is computed later. This is just an example. And if I have this here, which some of you will recognize as an MDS code, A, B, A plus B, and A minus B, then I can serve everything that is below this kind of trapezoidal or piecewise linear region, right? So what good that does to me? Well, depends what my requests are. And here I have assumed the following. I have assumed that lambda A is a Gaussian positive with these are the blue dots. So for blue dots, lambda A is Gaussian with a mean 4 and variance sigma square 4, and lambda B is twice that much. It's like some kind of a z-flow, like twice. The more popular one is considered twice. And the reason I took variance and the mean to be the same is because it's kind of a Gaussian approximation of Poisson arrivals. But these are just an example. It's not, don't look too much into these numbers, just something kind of reasonable. And vice versa. Vice versa means that maybe at some point in time, some A becomes more popular and B becomes less popular. So see, these red and blue clouds are symmetrical. And what I plotted here is 5,000 dots that for each, 5,000 blue and 5,000 red that I drew from this distribution. And when you look at the probability that a random assignment arrives, that we will be able to serve it, it's something like this. For these rectangular ones is about 0.7374. And then for ABA plus B is 0.87. Now, when I have 4 servers, even replication is doing well because of the symmetry in demands. But if I apply this coding A, B, A plus B, and A minus B, I get even more coverage, right? So request coverage basically means that which fraction of these requests will get served. So these skews in the probabilities that either one is more popular or the other are better handled by coding. And also in many of these emerging systems like Edge Cloud, we don't know really in advance what's going to be more popular. And so this fluctuating demands and fluctuating number of users is something that we would like to know how to serve better. So that's an example. And here is, I was mentioning service allocation. So if I now concentrate on this point 15, 0. So lambda is 15 and beta is 0. So lambda A is 15 here and beta, lambda B is 0. I say I can serve 15 users. And if you think about this a little, well, in A will give me 6. And I can also then read from B and A plus B, that will give me another 6. And then I'm left with A minus B, but that's just 12. How can I serve 15? And here, if I just have A, B, B, I can never get up to 15. And there may be situations where I really want to cover those points. Maybe this is not even the best example with these points, but there are skews in probabilities between A and B, and I want to get there. So 6 from here, if I read these 2, will give me another 6, but then I realize that I can actually split this bandwidth. So here is the bandwidth model. I will send a fraction. This is how I'm going to direct 15 users. I'm going to take 6 and send them to A. I'm going to get 3 and send them to B and A plus B. Then another 3 and send them to B and A minus B. I can solve these equations, right? And the last 3 I'm going to send to A plus B and A minus B, right? And from these 2 equations, A plus B and A minus B, I can again extract A and B. So, so this is an allocation. So is this really easy to find? Well, not exactly, but even some much simpler things are not obvious. Right? So this is a little bit of combinatorics. And what I'm going to talk about in this talk is a combinatorial approach to this service rate region problem. There is also a geometric approach. And among my students and collaborators, people have strong preferences, either combinatorial or geometric, depends how they think. And we also, in the very early work, we also used water filling, which information theorists will know that is. Okay, so the problem is the following. I have k objects, maybe these files f1 to fk. They are stored redundantly across n nodes. The size of each object and the size of data on each node are equal, right? So because they're linear combinations. Requests for object fi arrive at the system at rate lambda I, and each node requests are serviced at rate mu is equal 1. That means that actually in this previous, I divided everything by mu, and here mu was 6, so I normalized these things. And the objective is to determine the set of all rates lambda 1 to lambda k that can be supported by the system implementing some common redundancy scheme. Maybe it's the Simplex code that I've been mentioning, or MDS codes, or some others. I'm going to, in this talk mostly about Simplex codes, and I will define them so that if you're not familiar with them, you will know what they are. So this is when I have a scheme I can ask, because storage systems already implement redundancy, replication, coding. So what can I serve with them? And another is, what if I know my demands, right? What if I know these blue and red dots somehow, right? Or I know some kind of a region. Can I design a code that it's good to cover them? So these are two natural questions. And then there are some theoretical questions that kind of transpired when we started working on this problem. And I'll tell you about that. And some are open problems, of course. So I told you I would explain how we get this A, B, and A plus B region for this code. So if I map A into A, B, and A plus, if I map A, B into A, B, and A plus B and store on these three nodes, I can ask, what can I serve when lambda b is 0? And here it's easy. I definitely can serve part. These are these red requests from A. This is 1, or request. But think about that as normalized by mu, right? I can use the full bandwidth of this A. And then I can also use another one by reading A plus B and B. And so lambda smaller or equal than A is achievable. And because of symmetry, lambda b is smaller or equal than 2 is achievable. And actually everything is in between is. So information theorists like to think about, they talk about achievability and converse. And achievability is what can we achieve, and converse is what is that we know that we cannot achieve, right? And when these two things coincide, we have what we call capacity, right, in information theory. So, so here is kind of a converse which tells you lambda a plus lambda b has to be smaller than 2. And the reason is, so here I have labeled by b. So if I want to, so these are these correspond to this a, this middle one correspond to a plus b, and this is b here. And so I can read A from A, B from B, but if I connect to A and A plus B, that means I want B. Because if I wanted A, I would have not bothered connecting to A plus B. I have A on this side. And the same here, thing here. And so if I, we'll talk a little bit later about vertex covers of graphs, that means that all of this here, this is allocation. Whatever I'm reading in this A and this B and this B and this A, when I sum all of that, I get a lambda A plus lambda B. but I have already occupied the entire bandwidth of the left node and the right node. And their bandwidth is, each one has a bandwidth 1. So lambda A plus lambda B has to be smaller than 2. So this is that region. And that was the triangle in the that we had in the example. And now, what about a little bit more complex code? And what about a region? Suppose I have n servers and 2 files that I want to store A and B. How should I do that? Well, it depends what I want to achieve, right? What shape I want to achieve. And here are some other examples. Again, the first one is repetition, or what we call repetition code. I repeated A 4 times and I repeated B 4 times. And that is this green region, right? And so this is one kind of extreme. Another extreme, of course, I could have taken A everywhere, then I cannot serve B at all. Another extreme is, let's make a linear combination everywhere, right? A plus B, A plus alpha B. Alpha is an element of a sufficiently large finite field, or just think about that some number, so that all of these any 2 here are linearly independent, right? And therefore, any 2 I can solve them, because I can solve for alpha and for A and B, because these are any 2 of these equations are linearly independent. And coding theorists know how to do that. But now, each time I want to access anything, I have to contact 2 nodes. So if I want only A, right, I have 4 groups of 2, only A, there are no B people, so this is 4, the same for B. But I can never have them together be more than 4, right? Because each request costs me 2 reads. And so I get something like this, right? This triangle. And you would think, well, you know, coding does not seem to be a good idea. But if I just do a systematic code, meaning I have A and B here, and then the rest is formed as the equations above, so systematic Reed-Solomon code, I have this other region, this region here, which actually may be better than replication, although it's smaller, because very often I have, you may have A people and B people, and then together there is some sum of them, and you don't exceed that sum. So this definitely may have some advantages over replication because of these queues, right? This is 4.5 here. Whereas with replication, I cannot serve 4.5. And then the most surprising is this bottom row, which I have 3 A's and 3 B's and just 1 system of equations, right? And not only that I get up to 5 here, but this entire red region under this red curve is larger than what I get with replication. And when we got to that, that was a surprise to us, because in the beginning, all examples we could think of were examples that you can kind of get these queues, this kind of very polarized situations where you have many A people and very few B, or vice versa. But you would have to pay a lot when they are jointly high. But they're very rarely jointly high, just because, you know, this is some clientele, some number of customers that you're serving. And this was the first time that you actually get that you can get a larger region. So the conclusion here is that combining coding and replication is beneficial in multiple ways. And another thing that I would like those who are familiar with coding to notice that the service rate region depends on the generator matrix of the code, not the code itself. So for example, these 2 middle codes are, from a coding theoretic point of view, identical. They have the same reliability. I can afford to lose any 6 out of 8, and I would still be able to recover both A and B, which that is not the case for any other. And so in that sense, they're equivalent, but from the service capacity, they're not, right? One has this triangle and the other has this kind of trapezoidal thing here. So these are these 2 conclusions. And that's an open question, right? In general, like what is our goal? Maybe we want to achieve lambda b up to a certain point. Maybe we want to maximize the entire region. I'll talk a little bit more about that later. In the beginning, that's why I called an early theorem for any 2 objects. We were doing some kind of a greedy algorithm. We were just, send these users first to the systematic nodes, A users, and only if you are above certain capacity, send them somewhere else, and so on. And anyway, this was kind of a water filling. So for you who are familiar with the channel coding theorems in information theory, you will know maybe what I'm talking about. So we had something like this, which, settles the question, but it doesn't look that nice. And then we also, so this is for 2 objects, then we have an algorithm for 3. Then for MDS codes, we had this water filling, like a general algorithm, and so on. Which is all fine, but there are some kind of maybe more interesting ways to derive some of these things. And even how to think about that, right? Instead of applying what you know from information theory, like water filling, how to think about that? Like, can we answer some of these questions just by looking at the code very quickly? So if we have this code A, B, A plus B, and N minus B, so this is what I was showing before, this allocation for a particular example. So this is 2.5. Remember, it was normalized by 6 to 2.5 times 6 to give you this 15 that we talked about a few slides ago. Can I see immediately if there are no B users, how many A users can I get? No, I had to do this kind of almost tricky looking or tricks, performing tricks, right? Or how quickly can I find some tight bound on what is lambda A plus lambda B? So I know that if I have 4 servers and I only store A, then I can serve up to 4, right, for mu. Mu was 6 before, so 24, right, 4 mu. But what if I have this code? What is then this sum rate, lambda A plus lambda B? And actually here it turns out to be 3, but is it clear? How do I get that? And this is what we call the combinatorial approach to finding service rate region. And what I first I'm going to do, I'm going to make a graphical representation of an NK code. So code has a generator matrix G. Actually, why don't I, for people who don't know what a generator matrix is, let me show this example. So AB, and then I have AB, A plus B, A minus B. So that means that if you look at these columns, 1 is here for A, 0 for B. That corresponds to this A. 0 and 1 corresponds to B, because the bottom is B. 1 and 1 corresponds to A plus B, and 1 and minus 1 corresponds to A minus B, right? So this is a generator matrix. And so for each of these columns in the generator matrix, I'm going to have a node, right? So n nodes, this we call a recovery graph for the reasons that will be clear soon. N nodes corresponding to the n columns of G, right? Corresponding to each stored object, or some are coded. And then an additional node is added for each systematic column. This is to avoid those loops that I was showing before. So So there is an additional node, 0 for B and 0 for A, call it 0. So if two nodes correspond to a recovery set of data symbol X, then they're connected with an edge which is given a label X. Right? So, and this is an MDS code, so everything is going to be connected, almost everything, right? If I have A and A plus B, that's a recovery group for B, because when I XOR these two, I get a B. And in order to get a B, I have to connect to both. And similar on the A side, right? And if I connect to A plus B and A minus B, then I may either want A or B. It's not clear. But again, if I connect to A plus B and B, that means I want A, because if I wanted B, I would not connect to A plus B. I would just stay connected to B. And now, so we call it recovery graph because the edges correspond to recovery sets. And this is when we have recovery sets that are of size 2. So this is always when I have K2, or when I have simplex codes, which I will describe later, where the recovery groups have size 2. If that's not the case, then I'm not dealing with graphs, but with hypergraphs. But wherever I mention an edge, if you replace by hyperedge, things would generalize. So now, how is it helpful? So suppose there are no B people, no one wants B. So I remove all these black edges. So then I remain with this triangle and this A. And if I remain with this red triangle, I see that I can put numbers here, 1/2, 1/2, and 1/2 for A, that how much capacity I can put, and 1 here. And that gives me this 2.5. So immediately I am, and for those of you who are familiar with matching graphs, you will realize that I am essentially trying to, sorry, not matching, yes, trying to find the best fractional matching here, right? I'm trying to, so if I put weights 1/2, 1/2, and 1/2 on these A's, B's are gone. And these weights have to sum to the capacity of each node, which is 1. So that's one thing that I can see quickly. So I can, some of these points I can quickly determine. And capacity region, because of these linear constraints, is a convex polytope, so determining these points is a big deal. So I said service rates and fractional matching. What is fractional matching on a graph? Fractional matching assigns weights to edges of the graph, so that for each node, the sum of weights that are incident to that node, sum of the weights on the edges that are incident to that node does not exceed 1. And this is our capacity constraint exactly. So one of these constraints where we had this equation is exactly corresponds to that, right? So theorem, very simple claim, demand vector lambda1 lambda k can be serviced by the system if and only if there exists the fractional matching on G, so that weights on edges with labels I sum to lambda I. So I can put fractions here, and they can sum to lambda I, and I'm in business, as long as these weights that I put at each node sum to something that's smaller or equal than 1. So that's equivalent. So there is a rich literature on matching, especially when these graphs are bipartite, like in the simplest code case, then I can immediately get results. So now, what is vertex cover? So vertex cover of a graph G is a set of vertices, so that each edge in G is incident to at least one vertex in that set. So the cover here, for example, that I can have is, I definitely have to have A and B, because these edges are not incident to anything else. And it doesn't pay off to take just 0A and 0B, because I want to take as few edges as possible. So we want to minimize this vertex cover usually. And so I take A, B, and A plus B. So this is 3 edges are sufficient to cover these. And from that, I actually get the bound on the sum rates. So the sum of rates in the demand vector lambda 1 to lambda k cannot exceed the number of vertices in the cover of G. Now, a trivial cover of G is take all vertices. But in order to make this bound tight, we want to have the minimum set, which in general is not easy to find. It's a hard problem. But now the question is it hard for the codes, for recovery graphs? Well, some recovery graphs are bipartite, so it's not going to be hard. But how about some other codes? Well, in general, we can make some claims about MDS and some other codes. There is another approach that we call a geometric approach, which looks at these points here as points on the projective line. So I decided not to talk about that. It's very kind of attractive and easy if you're familiar with this notion and terminology. But if not, then it becomes a little bit too technical. And the more we looked into both approaches, the more we realized that there are equivalencies. So at the end, that will be some kind of a abstract solution, some kind of matroid that will be either combinatorial or geometric. Okay, so locally repairable codes. So I want to, now I mentioned a few times the simplex codes, which are a very nice class to bring about a number of things I want to talk about, including the connection with batch codes. Another thing is locally repairable codes are important in data storage, because if you're storing something on a disk and that disk is destroyed and you want to, or goes down for the moment and you want to repair, that's why it's called repairable, you don't want to go around the world looking for data. You want to have something local. Local means a small number. It does not mean geographically local or next to each other. So here, so that means that those recovery groups that I was mentioning are small. And they have a size R. And the size of recovery group is T. So whatever I was mentioning now is essentially a locally repairable code, recoverable code. And there is usually some price in the minimum distance that you have to pay by using these codes. It's not important for this talk. So here is our repair groups for A. So for some of you who are familiar with this structure, it's called the Fano plane. It's a finite geometry. And I know that my students who are here at the talk probably have heard about Fano's inequality, but it's not that Fano. It's this Fano here of this plane is the father of your Fano. Right? So this is Gino Fano, and the other one is Roberto Fano. And the generator matrix of this code is you take columns, the columns of the generator matrix are all strings, non-zero strings of length 3. And that can be generalized, can be strings of length m. Right? And here to your data correspond these outside vertices of this triangle. And in these, and these are the lines that connect them. And this inside line here, and that reminds me a little bit also of the geometric approach, is the labels 3, 5, and 6 all have 2 ones, right? And then there is 7, which has 3 ones, but that's an odd number of ones. So half of them have even, half odd. Well, actually, this is 2 to the k minus 1, so roughly. If you look at the recovery graphs, right? So this is how we often think about simplex code, right? If you look at the recovery graph, it takes some staring to see that it's bipartite, but we'll talk about that later. So this is how, these are your disks. you're storing here A, B, and C. Right? These were A, B, and C. And here is where you add them all up, and here is adding A and B, and therefore, so this is A plus B, therefore you're reading B. So this is your recovery graph for that code. And so your vertex cover is this 4 nodes. So the sum of all rates that that you can get here is smaller or equal than 4, because your vertex cover is 4. But this is a bipartite graph, so your also matching number is going to be 4. We'll actually prove it in a maybe more accessible way. So this can be generalized. So simplex codes, I can take any k, and I take all distinct non-zero vectors of f2k. So all strings of length k, right? And I can talk something about, again, my size of the recovery group is 2. If you are a computer scientist, you know this codes as Hadamard codes. So theorem, the service rate region of 2 to the k minus 1, comma k simplex code, that means k objects, 2 to the k minus 1 nodes, consists of all points lambda 1 to lambda k such that their sum is smaller or equal to the k minus 1. And achievability, how am I going to show that? I'll show you many times these with matching, but let's just look at your nodes, right? This is your capacity. And for A people, you're going to each time get lambda A, or lambda I divided by 2 to the k minus 1 of the, so whatever the request is, you will take that fraction of the capacity. And that means that since there are 2 to the k minus 1 repair groups, that you will be able to serve this lambda A. But then when you add them all up, that means that as long as their sum is smaller than 2 to the k minus 1, when you add them all up, this is going to be smaller than 1. And therefore, at each node, you are below the capacity 1. So you kind of slice your system here, corresponding to this number, lambda 8 or 2 to the k minus 1. And then let's say this would be lambda 1 over 2 to the k minus 1, and then lambda 2 divided by 2 to the k minus 1, and so on. And that's how you slice each of these bandwidths, right? And serve the approximate user. So that's how you achieve this. What about the converse, right? For the converse, we are going to make that graph, the recovery graph. And on one side, I'm going to have everything that has odd weight, and on the other side, everything that has even weight. And the edges are going to exist only between nodes that have different weights. Why? Because I cannot have, I cannot XOR 2 labels of the same weight, I mean, not the same weight, the same parity of the weight, 2 even or 2 odd, and get only 1, 1, right? A repair group, when I XOR these labels, it has to leave me with a single 1, otherwise, which symbol am I repairing, right? And therefore, it's a bipartite graph, and the way to cover it is by 2 to the k minus 1 nodes on one side. The other side has 2 to the k minus 1, right? On one side to the k minus 1, on the other side to the k minus 1 minus 1. When I add them, I get this. So I cannot do better than that. So that is how I prove the converse, and that's how we did it actually in one of the first papers, until we formalized everything with covers. combinatorial optimization on graphs. Suppose that lambda 1 and lambda k are integers. Then lambda 1 plus lambda k, if it's smaller than 2 minus k, implies that any size of 2 to the k multisets of object 1 is serviceable by this demand. So is there a connection between between this and primitive multiset batch code? And here, some of you are not going to know what I'm talking about, but is something like this. If you think about the service rate code that I just described, and put an additional constraint that each user occupies the entire bandwidth of the access server. And that is not a far-fetched assumptions that, for example, edge nodes with small servers, maybe you just occupy everything like that. In this scenario, batch codes are older than the service rate problem, and they were introduced through load balancing. So this is not how they were introduced. But think about whatever we said now. Instead, you cannot have multiple people taking here Coke. So this is only Coke, but only one at a time. And so I'm going to explain this on some examples, right? And you don't even have to know what the batch code is. It's a more general thing, which is on metric problems in graphs. So I'm going to ask a question, what about fractional versus integral service? So consider a simplex code, and I have a demand, and the simplex code is just ABC, right? Mapping into 7. So this is the code ABC, and I map this into these 7 disks. And there is a demand 1, 3, 0, meaning that lambda 1 is 1, lambda A is 1, lambda B is 3, and lambda C is 0. Or my demand is, so now if you're familiar with batch codes, it would be ABBB, which means that I have one fraction of users A and 3 times more users B. So how can I serve this demand? One possibility is what I just said, give 1/3 of the capacity of each server to A people, and 1/4 and 3/4 of the capacity to B people. And then you're done. Another possibility is serve A people all from here, from this systematic node A, and serve B people in the following way. Some of them from B, fraction of them from C and B plus C, and then another fraction A plus C, A plus B plus C. And here you're using the capacity of the entire system. And here you're using 1, 2, 3, 4, 5, 6, only 6 out of 7 nodes. So in a way, this is cheaper, right? And so this would be when you only can access the entire region. If I look at the recovery graph of this simplex code, on one side I have ABC. I have to have, in the recovery graph, I have to have all of these, plus this ABC additional nodes for them. So I have ABC, I have additional nodes for them, 0A, 0B, 0C, and I have others, right? And this is a bipartite graph. And I'm also, the red edges are recovery edges for A, they connect nodes that I need to read to recovery, and so for B and for C. So this 1, 3, 0, I can service by this fractional matching, 1, 4, 3, 4, 1 quarter for each red edge and 3 quarters for each blue edge. That means splitting the capacity of each node, 1 quarter for A people, 3 quarters for B people. Or I can do, this is an integral matching, meaning just 1 edge per node. A people are from here, B people, C people, and so on. And so these are 2 possibilities, right? Which one is better? Well, it depends what you want to do next, and I'll talk about that. And also in general, fractional matching is a linear program, whereas finding an integral matching, I'm talking about general graphs, may be harder, right? And so proving that this simplex code is a batch code was not an easy thing to do. And it was done by one of my hosts here, Hannah Mao, and his collaborators. And so the question is, can we somehow use this service and this linear program and make some conclusion about this integral, what we call integral service rate? And that's the following question in this particular, and that's an open problem. And it's a matching question on graphs that it wasn't asked before because no one was looking at a problem like this. So consider again our old friend, recovery graph for the simplex code. And I have lambda A edges. The lambda A is the sum of all on the weights of all red edges. Lambda B is the sum of weights on all blue edges, and lambda C is the sum of all green edges. Because these are the recovery groups, when I sum them, I'll get the total rate of for A people, total number of B people, and total number of C people, number of rate. And if this, and I know that this has to be smaller or equal than 4. And now the question is, if lambda A, lambda B, and lambda C are integers, is there always an integral matching with lambda A red edges, lambda B blue edges, and lambda C green edges? And so here, the sum of red edges is 1. So I want a matching which has 1 red edge in the integral, and here I have it. And sum of blue edges is 3. So I want this matching to have 3 blue edges, and there I have it. And C, I'm not concerned with here. And for this particular 7-3 code, we know it's true, and we can find we can start from anything of this sort that is integer, and run an algorithm and get to an integral matching. For larger, it actually, the state space explodes, so we don't know. But what we are asking is anything that is achievable by a fractional matching that sums to an integral on the corresponding edges. Does it always have a picture like this or not? Right. So that's the question that we don't know the answer. So this fractional versus integral has another interesting interpretation, and this is something that I've learned from Vitaly Skacek about a couple of years already, almost ago. They were looking into something called asynchronous batch codes, and that is if one of your users in the system leaves, can others or someone else who arrives use these freed resources? So again, if you look at this system, if you were serving users 3 times more B users than A users, right? And you could have served it by splitting like this, that we said, by this fractional matching, or you could have served it by this integral solution. Now, if A people leave, all A people leave, for example, you cannot do anything really, right? I mean, it's not exactly. You can serve some more B people because you're here not using A plus C. No, you're using A plus C, B plus C. So B plus C is freed and A is freed. So there is nothing you can do really with that. You could, if you now rearrange everything. So they call it asynchronous, but what if some users leave before others? So you would have to rearrange everything. So imagine you're in a restaurant and some people leave and you have to rearrange all groups around the tables to be accommodated, because you know that you can accommodate them, but you know you would have to do some other arrangement. So not really practical. And but if you use this fractional thing, you could. So Vitali here and his group, they were able to show that although you can serve any 4 requests and anything that adds up to 4 times mu, if you want to ensure that whenever someone leaves, you can serve anyone else, then that capacity, that bound drops down to 2. And that's not the case if you are willing to do this fractional thing. So I am here, I'm saying these are examples of other questions. So that's because I was saying that other. Okay, so this is another question is, what about if someone gives you a region, which is like this, lambda A is smaller than some alpha, right? It goes up to alpha, A people at most, that many are going to have. Lambda B, so B people at most beta, and their sum is bounded by gamma, because that's how many people lived in that place, right? Who are watching these A and B movies, for example. So what is the minimum code? What is the minimum storage that can support this number of servers that you have? And let's limit ourselves to binary codes. And the columns of the generator matrix can be only 1, 0, 0, 1, and 1, 1. So it's binary codes. I can either have A, B, or A plus B, and I can have multiples of those. So now I have to find multiplicities of each, and I can find some bounds that they satisfy. So there are some, this is this ITW paper that I was mentioning. Still, it has to be generalized for non-binary cases, etc. This is all very early work. And if I look at this here, so I am keeping beta and gamma 4, and alpha I am changing to be 4, and then 3, and then 2, and then 1. See how my coding schemes change. So here I have 6 nodes, and 2 of them are coded, right? That I am doubling everything. If I don't need this corner here, I can get rid of uncoded nodes. And I needed a coded node to handle this queue. Of course, I could have handled it by having even more other nodes, but I want to minimize the number. And as now I can drop one of the, here, I still have to keep a coded node, but I can drop one of the A nodes. Here I had 2. Here I can drop one of those, still keeping 3 Bs. I cannot go below 3 Bs because I have here to go up to 4, and so on. And eventually I don't need any coding because A is at most 1. So that's how it changes. There are some other questions that we can ask, and that is how adding one node can help. Should I add it, if I start with ABC, should I put another C? That way I would increase the capacity for C, or B plus C. This is how my region would look like, or A plus B plus C. So your reliability is increasing this way, meaning I can lose here any node. I can here recover C, but I would have to pay more. so if I don't need this reliability, maybe it's better, and I know that I'm looking for C, then maybe the second is better than the first. Whereas here, if I am encoding together ABC, then I am increasing, I'm able to handle skews in all of them. I can ask some system questions like how much it costs. Like if I want to achieve some of these points, I have to, for one, read more. To download A, I have to read B and A plus B, right? So I have to read more, and therefore I have to download more. I can ask these things, if you remember in the beginning, these points that I had that were zero, that they called, how many are covered. These were some other assumptions that we did. At that time, we called this sigma robustness, meaning if I can handle anything that adds up to sigma. Right? Okay, so to conclude, new applications such as, for example, edge devices, or here is an example of two cameras. One collects A, another collects B, and 4 disks. And what should I store? Maybe this is an intersection which is, it's more important to know. There are more people looking what A collects than what B collects, depending on the time of the day. And by changing coding and maybe combining coding and replication, I can shape this region, right? If I just do, again, if I just do replication, there is this square. So if there is anything that you would like to remember from this talk, it's just that what I put in here will change this region, right? If it's replication, it will have this square. But if I, for example, replicate 8 more and just put another B and just A plus B, then I have this Q, this red. And if they're more popular, but I really never get this triangle because I just don't have this many users together, then maybe this blue thing is the best. So there are various reasons. So now I am asking, how do I make this replication and coding not to make system more reliable, but maybe to make it better equipped to, or better suited for serving certain demands. So these new applications bring new questions. So needs for services of coding theory is gone. Every now and then coding is declared dead, but as long as we have errors or other things, that's there. We have written this paper at the archive posted, which is essentially a tutorial with many open problems. So if you're interested in this could be a good paper, good point to start. And that's actually all I had to say. So I don't know whether I should stop sharing the screen or.
So thank you, Emina. Can I ask, are there any questions from the audience? So I think we have time for a couple of questions.
Okay, then I'll ask my question. Yeah.
Thanks,
okay. Can you show the slides about fractional matching and integral matching? Yeah, because I think, yeah, especially the one with the simplex codes. Yeah, of course. Yeah, the bipartite graph. Yeah, I'm pretty sure you're aware, right, that for bipartite graph, fractional and integer matchings are the same, but this is somewhat different from the typical scenario, I guess. Yeah, so what was the obstacle of using that idea to show that simplex codes are batch codes?
So we actually don't, because we are just saying I think you showed that simplex codes are batch.
Yeah. But
but we were thinking, since we know everything about this fractional matching, if I only can show that whenever I have everything on A edges, these are A edges, sum to an integer, and everything to B, I know that these sums have to be smaller than 4. That's for sure. Or 2 to the k-1 in general.
Yes,
Here,
yes,
smaller
yes.
than 4. If I can only show that whenever I have these integers, there is a picture like this. But we don't. I mean, we have an algorithm for this one, but then if I want to follow that, it kind of explodes. So it would be nice to have some nice way to show it, because this is very easy. Like, this is like a 2-line proof to show that simplex codes are that simplex codes are this theorem, right? That was the theorem statement. So this, if you don't have the integer requirement, this is really an easy proof once when you realize that it's a fractional matching problem. But when you have a integer requirement, then we go to your proof, which is, serious one.
So my question is, because for bipartite graphs, it's well known that fractional matchings and integer matchings, there's no gap in between, and for any fractional matching, you should be able to convert to integer ones. But I don't think it's exactly the same.
Yeah, because for fractional matching and integral matching, we know that it's the same number. So there is nothing better that you can do with fractional than or integral or vice versa. That's true. But is it? It's more how these things are achievable.
To change it. Okay, we can take this offline.
Yeah. But that is one of my favorite topics. I would be happy to meet and talk about that more.
Okay, cool.
And I think actually what is written in the paper is okay, but then I thought about even a better way to.
Okay. Yeah. So, is the paper the last one, right?
Yes, exactly.
Emina, can I ask a kind of a basic question? So when you repeat, like when you have A, B, 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 can you so that's analogous to something like repetition coding, right?
Yes.
And then when you have the other combinations, that's like kind of slightly more sophisticated coding. So what I want to know is why do you actually even need to do? Because I noticed that in many of your schemes you have repetition, like you're looking at coding and redundancy. But if redundancy is actually a subset of coding, why can't we just generalize it and say coding?
Yeah, so we can, because this is all coding.
Yeah.
Let me just show this one. That is the one that maybe you were asking. This one. That is all definitely coding. So how we start? It's a little bit historical. So we started working on this because we were looking into queues with multiple demands, and we realized we cannot really. We were trying to estimate the response time, and the response time was so hard to derive that we started asking, can we even at least find when these queues are stable? And this is what in the queuing setting this looks like. The service rate region is where the queues are stable. Now, the performance evaluation, the performance people also discovered queues with redundancy, and they started calling them redundancy, right? And so when we published some papers, wrote papers and called them replication, coding, etc., they ask us, why do you call this replication? Why don't you call it redundancy? We call it redundancy. And we said, well, in the coding theory, we call this replication much before you. Okay. So now just because in various communities, this goes under the name of redundancy. We call it a redundancy scheme, as opposed to just coding.
Okay. Actually, I have two more questions. One is a technical question. I assume you're not taking latency into account, right? This is just availability, right?
This is just stability of queues, exactly. So for example, if you look, I'm not trying to preempt your question, but I just want to say, because you said, is it true? Like, for example, here, I am directing these 8 people, I'm splitting them between these. But I could have also sent them to, all of them to all these queues. That may minimize latency, right? Latency is what is it called? I would have to find the response time.
Yes. Yeah. So right now you're not modeling that, right?
No, that's an open problem too, and it's actually listed in this paper as how do we compute latency. Okay. Now, one of the people who works with me, Gauri, I think, and with some collaborators, they started looking a little bit into latency in some of the schemes, but they seem a little bit hard. Sorry for flipping all of this.
Yeah.
So the simple answer is no. We haven't looked at latency yet.
My last question
for some of these complex schemes.
Yeah. So my last question is more general. There's a few grad students here, so I'm wondering if somebody wanted to work in this area, what would you recommend? Like, I know you already pointed out some open problems, but let's say, are there any open problems that you would recommend students to
like easier ones?
Yeah.
Let me just show you, because I can go at the end, maybe click on this link and get to the paper, because I'm sharing the screen anyway, right? So you can see now the paper, right?
Okay.
So let's see, let me move this a little bit, PDF. So there is an entire section here. So the thing is, it's even undergrad. I had the RU students. Even to undergraduate, some of these things are easy to explain. So there is an entire section at the end which talks about open problems.
Okay.
And let me just maybe point out some of these to students. Yeah, this is a bit more code. Okay, ongoing and open problems. So there is, for example, that coverage. How do I compute these probabilities of how much I cover if I have given some probability distribution? Sometimes it's easy. Like, for example, once I was trying to check my numbers, and Chris Chang and Nick Burney, who were my students, they computed as we were talking, getting some of these. But in some other cases, it's hard. So that means how much of this area is covered, how much is outside, given some practical distribution, maybe some zip flow or something. So that's one thing. Then there is, how about cost? Because here, for example, each time in the repetition, whatever I download, I have to read only once. In coding, whatever I download, I have to read twice. So how do I compute that? Then the one that you mentioned, latency analysis, that is listed as an open problem, right? We said that we focused on the region, which is, and then analyzing latency, for example, designing delay optimal policies, because how do you delay this is sort of this allocation that we say it's throughput optimal. And delay optimal would be something else possibly. Then this question which I was, so this is coding theory and data allocation problems, how to design these codes, or if you have a code, how to design a generator matrix, which has the best service rate region. Then there is this one that we discussed. This is in the open problems. I just picked that because of Anmao interest. I kind of anticipated, so I picked that one to talk about. Then these, But if I want to have, there is the asynchronous also. Not if I want to have asynchronous, but how does a synchronous service rate region looks like? For that, I think I would have to know the entire matching polytope and what not only the matching number, etc. So all of these are there are many directions. Some are they're kind of easy to understand until you get past this original initial terminology. Of course, there's always, but some of them can be hard.
Okay, thank you, Emina. So yeah, I guess we'll point people to the paper. And I guess we'll have your video up soon so people can get the link.
Sure.
Okay, thanks.
Thank you very much.
So are there any other questions?
Hi, Emina. Can I ask a question? Yeah. Just now you have talked about the Simplex code, right? And we also know that for distributed storage system, we have the conventional regeneration codes and also locally repairable codes, right? So how's the relation between the Simplex codes and the regeneration codes or locally repairable codes? And is there any drawback of Simplex code compared to this conventional code?
So we did not look at all in at regenerating codes, right? We were concentrated on these recovery groups. And it doesn't even have to be local recovery. So for example, if it's MDS, recovery group can be any K symbols, right? But we didn't look at regenerating codes at all. So that is an open problem.
Okay. Okay, so it's not considered now.
No, no, we have not.
I see.
But yes,
yeah.
Interesting, of course.
Yeah, it will be interesting to explore, right? Yeah. And also, is there any possibility to do self-decision decoding right now for that kind of system?
With the purpose of
improving the capability for correcting number of features and etc. Maybe service rate region can also be improved with self-decision decoding.
Right, or actually any suboptimal. So for example, you can say, so these are, as we consider them, these were erasure codes. So you either recover something or you don't. But if you want some partial recovery, that's a good question too. So for example, you can say, you know, I can decode up to some probability or have some stop decision about these. Maybe that's good enough, or yeah, that would be another possibility to ask as a question. We haven't looked at that at all.
Okay. Yeah. Okay. Thank you.
Okay, are there any more questions? Okay, I think we're pretty much at the time now. I think it's pretty late for you, Emina. Thank you very much for a great talk. We really appreciate you taking the time to share and, you know, kind of help us spread the, what did I say, the joy of information theory and coding theory.
And I really appreciate that you are doing this seminar for spreading the word about information theory.